pick up from where we left off last time with practical transformers, and just quickly as a leading, because we've had a 2 week, 3 weeks since we last met. Difference between a real transformer and an ideal transformer as kind of the opposites of the assumptions that we made, and actually do resistance to core infinitely variable, i.e. there is a limit to the amount of magnetism you can pump into the core. After that, saturates by primary, completely captured by the secondary. There's a leakage flux. Equally, not all of the secondary is captured by the primary either. So there's not all the flux is linked would be the simplest way to say that. Some of the flux leaks away and is not used in any way in a transformer action. Iron cores produce eddy currents in hysteresis transformer, so that's why it gets hot. The power loss. Also need to magnetize the core and current as well. So what we're going to do is develop a model to calculate loss. By taking some measurements and find the for that load up, meter, find what's the remainder of them. What we've got is overall current flowing when the secondary is disconnected. Part of that I'm not sure where you still paid up linked to the opposite coil. In coil 2, Bob Flux. Another coil in 2 turns. that. We terminals transform the all right, and that's have a what? Well, yes, you can measure it. But well, yeah, you can measure it, but the best way to get the parameters is to get them by doing, and that's how we're going to do it, is by doing open circuit, short circuit test. Yeah. So you take some measurements open circuit, and then you short circuit the secondary and take some more measurements. Obviously, being very careful about how much voltage you apply when you short circuit the output, and then from those readings you can calculate the values you need to put in the primary and secondary for a reasonable model. Yeah. Okay. So what we'll do is have a look at an example problem. I find my secondary winding transformer has 180 turns. Let's start to write this down. So N2 equals 180. When the transformer is under load, secondary current has an effective value of 18 amps. So I2, 18 amps. F, 60 hertz. Always useful to pull out the information from a written question. Furthermore, mutual flux peak value of 20 millivabers, and the secondary leakage flux is equal to 3 millivabers. Calculate the voltage induced in the secondary winding by its leakage flux. So what we need is this formula for the voltage of leakage flux 2, leakage flux in the secondary, and that's that 4.44 F N2 flux 2. It's the one you want for that. Yeah. So that's going to be 4.44 times 60 times 180 times 3 times 10 to the minus 3 millivagers. Yeah, let's have 143.9 then, Mike, shall we? Volts. Yeah. Okay, now with the information we're given, how do you think we can calculate the value of each inductance? So we're looking at what is X2, the leakage inductance in a secondary, from the information that we got. B. Yep. So EF2 we just calculated over the current. We got this inductor that's got EF2 across it and a current I2 going through it. Yep. So that must give us reactance. It's 143.9 divided by the current which was given, and that was 18 amps. $7.99. Okay, and then C, the voltage induced by the mutual reactance. That's the voltage. Just go back to the previous diagram. The voltage here, E2. No, we're assuming at this stage we've got no resistance in this problem. We're just looking for reactance. So that first voltage we calculated was just the volt drop across that reactance. All right. So again, go on, James. Yep. Instead of 3 millivagers. Yeah. Yeah. So we want this formula here again. 4.44 times F, the frequency, times N2 times the mutual flux. 4.44 times 60 times 180 times 20, I think it was 10 to the minus 3. $959 volts is what I've got. Yeah. I don't know how close that is to what a real transformer would be like. I've got question come out of a book. That's not one I've written myself. So sometimes they tend to use realistic values. Sometimes I'm doubtful, and I'm a little bit doubtful about that one. But that's pin or buy for the purposes that serve. All right. Where I'm using big transform, when we look at analysing, I think the next example, I did look up and try and find some typical values of a real transformer, so it's a bit more realistic. There's a table I found in a book, and that kind of told you see how them values changed as the VA went up for bigger and bigger transformers. It's quite useful. All right. So that typical calculation, you might get one like that in the exam. You never know. Okay. So yeah. Assuming, say that's our model, yeah. Yes, but you'd have to consider whether they were in phase with each other. Yeah. Alright. Which is kind of why I haven't done that at this stage. Okay. So, if we now consider both of the two model considerations that we've considered together, the full equivalent circuit for a complete transformer is that. So on the primary side, we've got a primary current flowing, okay, XF1's representing the leakage flux, R1's representing the resistance of the windings, RM, core loss, heating, XM, magnetising current. In the middle, we've got our old friend, the ideal transformer, with its ratio A is equal to N1 over N2. Output terminals of that are E2. I go with EP for E primary, the terminals that you can put your meter on. E1 being the input to the primary side of the ideal transformer. E2, output of the ideal transformer. We've then got XF2 representing the secondary leakage flux, R2 representing the resistance of the secondary windings, and we then got E secondary across the secondary terminals, and then a secondary current and any load that we may wish to base upon. Alright? And again, I've clarified there that the terminals EP and ES are the only voltages apparent to the outside world that we're able to measure with a meter. Yeah, we can measure the currents, we can measure those voltages at those terminals, we can't measure anything else. Okay? Well, I thought there was another problem on there. There is in your notes. Is it? No, they were the tutorial questions. Hang on. As 12 ohms, X1, 36 ohms, EP, 11 kV, R2, 0.008 ohms. Quick question for you. What do you reckon that, based on resistance to the windings, do you reckon that's a step up or a step down transformer? if you think about copper winding, what would make the resistance less? Big cross section and or less turns. So that suggests step down, doesn't it? Yeah. And the current's going to be more. Yeah. So just worth, these underlying things can help you see through problems and see whether you're going the right way. So I thought I'd just ask that. R2.008, X2 0.03 ohms, and ES is 400 volts, so we're right. And nominal rating (100 kVA). I'm just going to go through what the question was asking for, one thing at a time. We'll work through it. Okay. First of all, I asked find transformer ratio I, little a. How can we, with the information given, how can we find the transformer ratio? Put the two voltages as the way. I wouldn't trust the two resistances. Well, we'll have a look at that in a minute. So I is if I step down, is A going to be a whole number or less than 1? A is usually N1 over N2, so if we're going to use the voltages, it must be E1 over E2, mustn't it? Same way up. Remember, and again, that ideal transformer equation. So A, in this case, is E1, oh sorry, E primary over E secondary. Just remember my terminology. Primary was 11,000, secondary 400, $27.5. I might have picked the blinking whole number for our first example, mightn't I? Okay. Never mind. Sorry? Greater than 1 is step down, yeah. Yeah. No, I is 27.5. Remember the reason we go with A is because in a minute we're going to be doing this transfer and impedances thing. We want to multiply by either A or A squared. And that's a lot easier than trying to multiply by EP over ES squared. Yeah, or N1 over N2 squared. We have no way of knowing how many turns there really is on either of the windings because we haven't been told. But we can do it from the two voltages. The other way we could do it is from two currents if they were given as well. Yeah. So the closed circuit, the test on the transformer open closed circuit is, I think, is to use two currents. Alright, B, next thing they asked was full load current I2 and value of load that would draw this current. How can we get to that from the information that we know? No, we haven't gotten that. What is this? No, it ain't Q. It's not Q. S. Nominal rating S is equal to 100 kV. What's important about that? It's the same on both sides. Yeah? So, we've got the nominal secondary voltage and we've got S. Yeah? So we can find out at that voltage what the maximum current would be, because this is that voltage times the current, isn't it? Yeah? So we can go S is equal to E secondary times I2. Yeah. Therefore, I2 is equal to S over ES, which is 100,000, 100 kVA, wasn't it? Yeah. Divided by 400 equals 250 amps. It's a big old transformer, this one. What's the primary current on the transformers at the station? You know? You'd have to have a look. Yeah. Because you're generating at 19. Yeah. So, yeah, it's interesting to know these things, know how big the numbers are when you get into real stuff, station like that. Alright, so secondary current is 250 amps. Okay, now we want to know, what load, what RL would draw that current at that voltage. So we can just go RL is equal to E secondary over I2. That's the 400 over 250 equals 1.6 ohms. Yeah. Yeah. Right. So, question? Value of 3. Transfer to primary. So we're going to analyze this. We've got that one, and that one into the primary side. Okay. So we'll start with RL. We're going to find what we like to call RL dash. Remember that? Remember that, Mike? Christian? Yeah. How do we do that? Anyone remember? Now, it's a good while ago now, isn't it? We're multiplied by, six. And 210. Yep. Two is equal to a squared times R2, 27.5 squared times and then lastly x2 dash is a squared x2 is 27.5 squared times 0.03. Yeah, 7. Okay. As I don't know when I turn the video off, I'm just going to summarize that up again. We've got this model where we transferred the impedances over to all into the primary. We're going to find the primary current at the nominal primary voltage. So it's found the total impedance. We can take the We can take all of the in-phase components and all of the out-of-phase components separately, multiplied by J, combine them together to get a rectangular total impedance, and then we've converted that to polar, and then used that in Ohm's law to calculate primary current of 8.94 amps, angle minus 2.7. The negative angle, suggesting that current lags voltage, fits in with civil for an inductive circuit, and the fact that this is much lower than the secondary current we had for full load suggests that's correct, because we know we got a voltage step down transformer, so the current must be step up. Yep. Okay. The next thing I asked for calculating was secondary current. So this is E. Under the same conditions. How can we do that? I.e. the nominal 11 kV on the primary terminals and fully loaded. Remember, this value for our resistor we calculated for full load, nominal full load current in the secondary, weren't it? Yep. So we're going to go with those same, keep the conditions the same. How do we find, knowing that we now know the current flowing here, IP, how can we find the current flowing in the secondary? How do we transfer current? We know what's going to make it bigger, so what do we think we need to do with A? If you think of it like that, we know it's got to be bigger. A is 27.5, so that's the ratio, isn't it? Anything on that side, any current on that side is 27.5 times bigger. We must have to multiply, mustn't we? So the way into this is that I2 is equal to I primary. Hang on, no, I'm going to write it like this, is equal to A times I2 dash. I2 transferred to the secondary, and I2 dash is equal to the primary current we just calculated. Yeah? You get that or not? Yeah? Therefore, I2 is equal to 27.5 times 8.94 angle minus 2.74. There's no angle to the ratio, so it doesn't change the phase. So the currents in the primary and secondary in phase with each other. That's going to be equal to 27.5 times 8.94, which is 0.9 amps, angle minus 2.74 degrees. So the nominal secondary current is 250 amps. Because of the side, we're losing about 4 amps. Yep. Well, the losses in both sides. Yep. Okay. Right. And lastly, F, current power to the load under these conditions. How are we going to do that? Looking at the diagram, we now know we want to know the S associated with that component. Yeah. So what's that voltage across there? Yeah, well, we'd call it ES, because that's after the two losses in the secondary, isn't it? ES dash, isn't it? Yeah. Okay. If we find that and then multiply it by the current, they're going to be in phase with each other because that's resistive. You don't have to worry about angles. We can then just get S from the current and voltage. Okay, so ES dash is equal to, I'm going to do it in terms of, that's going to be the primary current times RL dash, isn't it? Yeah. We're still got everything on that side of the transformer at the moment. So that's going to be the primary current is 8.94. Angle minus 2.74 degrees. Going to multiply that by RL dash, which was 1210. What we got? 10,800. Got? Nah, 10,800 will do. Volts. Angle. Minus 2.74 degrees. Yep. Now, how do we turn that into ES? We're transferring voltage, not impedance. What's got to happen to the voltage? Up or down? Step down transformer. This help you to remember this. Must be ES dash divided by A. It's going to make it smaller. Yep. So that's the 10,800 angle minus 2.74 divided by 27.5. And the angle is still minus 2.74 degrees. Yep. So now we've got that, we can say, ignoring the angles because they're in phase, the current and voltage in phase, S load is equal to E secondary times I2, just the magnitudes, 392.7 times current, which was 245.8 amps, equals we got 96.5 kVA. Yep. So if they think us nominally 100 kVA, it's pretty efficient. 96.5 of 100, 96.5% efficient at transformer. And those values were taken from ratings of a real transformer. I always used to think transformers were a lot less efficient than that. But that's with it nominally fully loaded. Yeah. Okay with that kind of calculation? Yeah. I think what we'll do now is just take a 20-minute break for a coffee.